Hello and welcome to Aughton Math. In this edition of Aughton Math, we're going to talk about composition of isometries, the last video in our series on transformations. All right, so our objectives: understand the definition and vocabulary around composition of isometries, identify the isometries required to map one figure onto another, and given a set of instructions, find the coordinates for an image after transforming it by a set or sequence of isometries. All right, so isometry is a transformation that preserves length and size. So translation, length and size stay the same. Rotation, length and size, same. Iso means same. Rotation as an isometry. Reflection is an isometry. The one isometry, non-isometry that we've covered in transformations will be dilations. Okay, so a composition of isometries is a layering or sequencing of more than one transformation for a given preimage. So we take one preimage and we transform it using an isometry, and then again at least one more time, so more than one sequencing of isometries that are connected back to back. All right, so let's take a look at how that might look. I have my rectangle ABCD. I'm going to reflect it across the line of reflection. Becomes A prime, B prime, C prime, D prime. I then translate it A double prime, B double prime, C double prime, D double prime. And then I am going to rotate it to become A triple prime, D triple prime, C triple prime, and B triple prime. So I reflect and then we translate. And so I'm using each of the three isometries. And then we rotate. And I end up with my image based on a sequence of isometries that's a composed image. All right, so this is just an example of how composition of isometries might work. All right, so I want you understanding the composition of isometries works in a certain way and knowing how to write a command for a transformation. I want you to tell me the two commands that would get the preimage ABCD to map onto A double prime, B double prime, C double prime, D double prime. And then as I mention this, I will say that sometimes the sequencing does not matter and sometimes it does. And then sometimes you can get to a mapped figure using different sets or sequences of isometries. So that being said, there's more than one answer to a question sometimes with the composition of isometries. So I'm going to pause here while you figure this out. All right, so this is what I determined for the sequence, and you can, and probably I'd prefer that you somehow denote the sequence 1, 2, or put them in some type of order so that there is a sequencing that's in numerical order or from top to down. So I say translate x, y, x plus 3, y plus 0, and you don't need to put the plus 0 here if you don't want to. And then we're going to rotate it plus 90 degrees about the center of rotation 3, 3. Now you could rotate first 90 degrees, but then you would need to change the center of rotation to 0, 3. So just be careful if you change the order, the sequencing of this composition, you may need to change some of the values that I've identified here. In this case, it would be the center of rotation. Okay, so let's also talk about some cool things that happen with compositions. So composition of reflection across two parallel lines is a translation. So if I reflect and then reflect across two parallel lines, I end up with a translation, so just a shifting of each of the points in a figure by a given xy amount. And so again, we can see this here. If I draw my line here and then two parallel lines, and I reflect B, and then again, so P to P prime to P double primed, you can see that the two reflections across two parallel lines ends up being a translation. All right, a composition of reflections across two intersecting lines is a rotation. So I start with A, rotate it around, reflect it across this line, we'll call it line M, and then reflect it again across line L. Now, these two lines are intersecting, and I end up with a rotation of the two figures. So composition of reflections across two intersecting lines is a rotation, and then the composition of reflections across two parallel lines is a translation. Okay, we'll skip that, a little bit more detail than I'm going to provide, at least in this video. All right, so here's a command. I have a figure triangle fun. Here are the coordinates for fun. We're going to reflect over the x-axis, and then we're going to translate +2 minus 3, and I want you to come up with the composed figure. All right, so the first thing we're going to do is we're going to reflect over the x-axis. U becomes 1, 3, U prime becomes 1, 3, N prime becomes -5, 1, and F prime becomes -3, -2. And I'm going to take that figure and I'm going to translate it +2, -3, +2, -3, and double primed becomes negative, where are we here? N double primed, I'm going to have to pause for a moment. Okay, so N, I've cleared up the diagram here. N double prime becomes -3, -2. F double prime becomes -1, -5, and U double prime becomes 3, 0. So this is the ending composed figure. All right, so last part of the class, I'm gonna have you reflect point A, which has a coordinates of 2, 3 across the line of reflection. Y is equal to x plus 3. Translate A primed +3 minus 5. Rotate A double primed 90 degrees about the point 1, 1, and then find A triple primed. And I want you to do this all mathematically. So let's see if you can handle that this transaction for the composition of this one point, and then I'm going to come back and go through the answer with you. Okay, so we're going to recall we've done some work before this about reflecting points across any line of reflection. So we know that the reflected point A to A prime, which we haven't figured out mathematically yet, is the same distance to the line of reflection as it is to the reflected point. So if I were to draw a line segment from A to A primed, we know that the line of reflection would be the perpendicular bisector of A primed. All right, so not knowing A primed, we can figure out what A primed is given the line of reflection and A, which is 2, 3. All right, so we know that the line of reflection is y is equal to x plus 3. And we know that A prime is perpendicular to that line of reflection. So we know the slope of A to A prime is going to be -1. We know all we need for a line is a point and a slope. So we have the slope -1, and we have a point A, which is 2, 3. So we're going to use a point slope formula to solve or write the equation for the line that goes through A and A primed. So it would be y minus 3, so 3 here, is equal to -1, the slope that's the opposite reciprocal of the line of reflection, times x minus 2. And we're going to simplify that. Y is equal to x, -x plus 5. So now we have the equation of A primed, and then we have the equation of the line of reflection. So here is the equation of A primed, and here is the equation for the line of reflection. And we're going to solve for x. So we end up with x plus 3 is equal to -x plus 5. We want to find this point of intersection. 2x is equal to 2, x is equal to 1, and y ends up being equal to 4. All right, so now we have the midpoint of A primed, and we have an endpoint A. We can find A primed, which is the endpoint of the segment given one endpoint and one midpoint. So let's solve for x first. 2 plus x, so we have the midpoint formula. 2 plus x primed over 2 is equal to 1. So 2 plus x primed, which we don't know yet, over 2 is equal to 1. And we solve for x primed, we get 0. Similarly here, 3 plus y primed, which we don't know yet, over 2 is equal to 4, that midpoint. And we solve for y primed and we get 5. So A primed ends up being 0, 5. We can solve this mathematically. So we have our first piece of the composition. So A primed is 0, 5. Now we're going to translate A primed plus 2 minus 5. So 0 plus 2, and then minus 5, and we end up at the coordinate A double primed, which is 2, 0. Okay, the last part is to rotate that around the point 1, 1. And we know that the center of rotation has to be the perpendicular bisector of the perpendicular bisector of 2, 3, and 2, 0. We also know that we're rotating A primed 90 degrees, right? So when we rotate the A prime to A triple primed, we're creating a right angle here. So we can take this point, which is 1, 1, and A double prime, which is 2, 0. We can find the slope of this line here. All right, so 1, so again, this is 1, 1. I don't have it written down here. 1 minus 0, here's the 0, over 1 minus 2 leaves us with a slope of negative 1, which means the slope of this line here is going to be positive 1. All right, so we have a point and a slope. We can find the equation of this line. Y minus 1 is equal to 1 times x minus 1. So the slope of this line here is y is equal to x. All right, so we know that this line is y is equal to x. And now I can use what I know about circles in order to find this point here, right? Because this, we're forming a circle through the rotation with a radius that's equal to 1. I'm sorry, a radius that's equal to 2 units. Excuse me again. Radius that's equal to, radius squared is equal to 2 units. So we have, here's 1 and 1. This is going to end up being the square root of 2. So that value squared gives me 2 here. And I'm using my formula for a translated circle. So 1, 1 is the center. So x minus 1 squared plus y minus 1 squared is equal to 2. I know that y is equal to x here, so I'm going to substitute x in for y. X minus 1 squared plus now substituting x here. X minus 1 squared gives me 2 times x minus 1 squared is equal to 2. I'm going to divide by both sides by 2. I end up with x minus 1 squared is equal to 1. And then I'm going to solve for that value. X minus 1 squared, take the square root of this value. I end up with plus or minus 1. For now, we'll just use plus. And then I'm going to add 1 to both sides, and I end up with x is equal to 2. All right, if x is equal to 2, I can substitute that back in and solve, right, because I know y has to be equal to x. And so y is equal to 2 as well. All right, so a little bit complicated problem using what we know about circles and quadrantal angles and how they affect the rotation value when we rotate 90 degrees about a point. All right, that's it for this edition of Ott and Math. Thanks for joining. Let's talk next time when we now get into just the basics of geometry in the next edition of Ott and Math.